in the Bode plot of a unity feedback control system, okay, the value of phase of g of j omega at the gain crossover frequency is minus 125 degree. Okay, now find phase margin. So this is a question. See now. Okay, if we look the Bode plot, this is a magnitude plot, and let this be for the phase plots. Let's suppose this is minus 180 degree. Okay, so I have at gain crossover frequency the phase is minus 125 degree. Let's assume that Bode plot is something like this. This is my gain crossover frequency WGC. At gain crossover frequency I have some phase. Okay, let that phase be phi n. Okay, now gain margin is, the phase margin is this particular value. Okay, from this point to this point how much is the phase difference? That is my phase margin. Okay, so at omega gc phase is equal to minus 125 degree. Thus phase margin is equal to minus 125 minus of minus 180, which will give me 55 degree. Okay, so this is the phase margin for the question which is asked. Okay, simple. Now another problem. First, algebraic equations are given. From these algebraic equations I have to draw a signal flow graph, and then I have to find the gain which are asked in the question. Draw a signal flow graph for the following set of algebraic equations. Okay, y2 equals to ay1 minus gy3. y3 equals to ey2 plus cy4. y4 equal to ty2 minus ty4. Okay, I have to first draw the signal flow graph, then after drawing the signal flow graph find y2 by y1 and y3 by y1. This is a subjective type question asked in GATE 1998. There are 4 nodes, y1, y2, y3, y4. Let this go to y4 with gain 1. Let this come from y1 gain 1. These both are same. Now I have to get y2 from y1 and y3. So y1 it is direct multiplication by a, and from y3 minus G. Okay. Now Y3 is sum of Y2, this is E, and this is C. Okay. Y4 is from Y2 and Y4 itself. This is my D, and from Y4 this is, okay. So this is a signal flow graph for the given set of algebraic equations. Now to find Y2 by Y1, Y2 by Y1 is equal to A. Okay, upon this A is one forward path and then the delta. Delta we have to find separately. A is one forward path. To this forward path, is there any non-touching loop? Yes, it is there, and that is minus D. 1 minus minus D. So this is A of 1 plus D upon delta. Now to find delta, we have to take all the loops. 1 minus single loop, one is minus D, then another one is minus EG, another one is C, B and G. Okay, minus C, B, G. Okay, this is one. Now two non-touching loops, yes, they are there. One is EG and the one is C, plus minus EG minus D. So I can write this as 1 plus D plus EG plus CBG plus EDG. Okay. Thus overall my Y2 by Y1 is equal to A of 1 plus D upon 1 plus D plus EG plus CBG plus EDG. So this is my Y2 by Y1. Similarly, this delta will remain same. Now next, in this to find Y3 by Y1. Delta will remain same, only the number of forward paths will change. So for Y3 by Y1, one forward path is AE, another one is A, B and C. AE, again same 1 plus D, another forward path is A, B and C, A, B, C. Numerator will remain same, and that is equal to 1 plus D plus EG plus CBG plus EDG. So this is the solution for the problem. One more problem from the same year 1998. The statement for this problem is: consider the system shown in figure. Okay, for this system, determine the value of A, where A is some constant, such that damping ratio (0.5). Okay, for this particular value of A, also find the rise time and maximum overshoot. Okay, if input is step input. Okay, now system is this. Okay, the system is shown here. Now the solution. The overall transfer function, which is Cs by Rs, is equal to 16 upon S into S plus 0.8 plus 1 plus As. This is equal to 16 upon S square plus S into 0.8 plus A plus 1. Okay. Now omega n square is equal to 1. Omega n is equal to 1. Now this is, since this is a second order equation, 2 zeta omega n is equal to 0.8 plus A. Now I want my damping ratio to be 0.5. 2 into 0.5 into 1 is equal to 0.8 plus A. This implies my A is equal to 1 minus 0.8 is equal to 0.2. Okay, thus we got the value of A. Now with this value of A, looking for the second order system, if the input is a step response, then I have to find the rise time and the maximum overshoot of that. The rise time Tr is equal to pi minus phi upon omega d. Phi equal to tan inverse under root of 1 minus zeta square upon zeta. Omega d is equal to omega n under root of 1 minus zeta square. Okay, so this will give me tan inverse under root of 1 minus 0.25 upon 0.5. Substituting this value of phi, and omega d is equal to 4 under root of 1 minus 0.25. Okay. Substituting this, I will get my Tr as 0.6 second approximately. Okay. Now for maximum overshoot, MP is e to the power minus pi zeta upon under root of 1 minus zeta square. Substitute the value of zeta and get this is 0.546 or 54.6%. Okay. So this way the value of rise time and maximum overshoot is just found using the formulas. Okay. Yes. If we remember the formula, it's well and good. Otherwise we have to derive it in the exam. So this was a set of problems from the other years of the GATE exam.